In this podcast and in class, we'll be learning about the physics of galaxy formation. And this will be happening in a cosmological context, and so we'll be able to put together cosmology and our understanding of physics and galaxies to get some idea of how galaxies form. And so we're going to be looking at these following goals during the podcast and the class. The first question is, well, why do galaxies exist at all? So I want you to stop for a second and to go to your textbook and to review our idea of the evolution of the cosmos, and to get some idea of to remind yourself how the universe evolves as a whole, all the way from the very earliest times where inflation happens through to the creation of heavy elements, the creation of protons and neutrons, and then the synthesis of deuterium and helium, a little bit of lithium, and then finally to the era of recombination, where the electrons combined with the nuclei to create atoms for the first time. This is, just to remind you, this is the structure in the cosmic microwave background that we see at these early times in the history of the universe. And you'll remember that these bright and dark spots are the denser and less dense parts in the universe, but that these density variations are only 1 part in 100,000. And you'll remember that we were discussing how these fluctuations are seeded by quantum fluctuations in the very early universe and are then inflated to scales that are comparable to the observable universe. And that then these slight over and under densities, the overdensities, collapse into the galaxies that we have today. And we're going to talk about that process. And so the physics of how these less dense and more dense and less dense patches of the universe collapse actually has a lot to do with our understanding of the evolution of the universe. So the evolution of in the evolution, you'll remember that we have, these different possible evolutionary paths of universes that are more dense, have critical density. Remember, this is the density that's required to just have it always continuing to expand, but always slowing down more and more and more as time goes on. And then the coasting universe, where you don't have enough matter to stop collapse. So it turns out that these areas that are overdense, they act like little overdense universes, and they expand, and their expansion stops. They turn around and collapse to the present day. And so galaxies, right? When you think of a galaxy, at some level, what you're looking at, what we're thinking about, is a little patch of the universe that's too dense, and it expands at the beginning, but then it's got so much material in it that expansion slows down, it turns around and collapses, and it does so actually long before the present day. So the Milky Way galaxy used to be an expanding patch of the universe that slowed down and collapsed, and now we're in a little patch of the universe that has that then forms this little dense nugget of stuff that we call a galaxy. There are areas in the universe with very little stuff, and those don't have enough matter to turn around and collapse, and so they are expanding. Still towards the present day. So at some level, you remember the balloon analogy for the expansion of space. There are little, the balloon analogy isn't perfect because it has a surface that's kind of constrained to have an overall geometry. What's happening here is that there are actually little pieces of the universe that are expanding but then turn around and collapse again. So it's like a little, you have an area that pinches on a balloon and kind of ties off, and then the balloon keeps on expanding around it. That's kind of how we should think of these galaxies in a cosmological context. I'll show you an animation about this in a minute. Now, dark matter is a key part of this, and there's some math that goes into this. We're not going to talk about the math. What I want you to know is that the growth of a galaxy is proportional to the scale factor. Remember the scale factor, 1 over 1 plus the redshift, which tells you something about the, essentially the size of a standard, it tells you about the scale of the universe. A little wave, you can remember, could be painted onto space-time, and it expands as space-time expands, and it's essentially that wave, the length of that wave is proportional to the scale factor, or 1 over 1 plus the redshift. And the growth of a galaxy turns out to be proportional to the scale factor, for reasons that we won't go into. The important thing here is that this structure that we see in the cosmic microwave background is only 1 part in 100,000. It's at redshift of 1,000, so this structure should be only 1,000 times more prominent today. It should be 1 part in 100 today. So the universe, if it had no dark matter and it had the fluctuations we see in the cosmic microwave background here, right, we would expect the universe to be completely smooth to 1 part in 100 today. The universe is not like that. The universe is richly structured. There's galaxies and stars and planets and stuff. And so, and these structures manage to form because the fluctuations we see here in the cosmic microwave background is the fluctuations in normal matter. We know from the existence of galaxies today and from computer models of how galaxies form that the dark matter fluctuations have to be much larger than these than the fluctuations in the normal matter. And they're, it actually has a lot to do with, you remember dark matter doesn't feel electromagnetism, and so it only feels gravity, right? And so when there's a little overdensity in dark matter, the dark matter collapses onto it with no reason to really stop collapsing onto it. Whereas normal matter, that matter as it collapses, it heats up. The photons, it starts emitting blackbody radiation, right? Thermal radiation, and that kind of produces a pressure which then causes it to stop expanding, or to stop collapsing. Excuse me. And so there's the fact that normal matter feels the electromagnetic force, and it's an ionized plasma, and there's a lot of radiation around. Those all stop the normal matter from collapsing, whereas the dark matter can collapse before this redshift of 1,000. And so the key thing here is that dark matter really does seed the formation of galaxies, and it's only because of the only way that we can connect the tiny fluctuations we see in the cosmic microwave background with the existence of galaxies today is through this dark matter. So this is a movie of galaxy formation in a cosmological context. Here we have the scale factor. Here we have the redshift. And somewhat unusually for this, we're actually going to look at a physical patch of the universe. So this part starts out dense. There are only particles here in a certain region, right? So in practice, the whole universe would be filled with this stuff. It's just for computational reasons that's been limited to this region. Now we're going to go forwards in time, and this universe is expanding, right, as it should. But you can see that there are parts of the universe that are dense and that have started to recollapse, and these are some of those. Right, so if we stop here and go back, right, you can see that they're, essentially on the kind of surface of the balloon, but that there's matter flowing in to these into these areas, right? So this is what I should say is that what you're seeing here is dark matter particles, the distribution of dark matter particles, and just the color is telling you how many there are per unit volume. So the dense parts are yellow, and the less dense parts are purple and blackish and bluish, right? So as the universe expands, these overdense pieces of the universe, the galaxies, they collapse. They collapse into larger and larger into larger and larger galaxies. And you can see also that these overdense patches, they feel each other's gravity, and they actually end up merging and coalescing into larger and larger units as time goes on. And so all those different overdense patches at early times actually end up collapsing into one, well, they're almost collapsed into one big unit by the present day. And this is now what it looks like in the present day, and we're just kind of zooming around and looking. These are in the advanced stages of merging, and quite soon will turn into just one big galaxy. So we've looked at why galaxies exist, and we've realized that inflation is a key part of this, that inflation gives you the overdensities that end up collapsing into galaxies, that dark matter is a key part of this, that dark matter is much more structured than normal matter at early times, and that acts as the seeds for galaxy formation. And then we've seen that we expect galaxy formation at some level to be driven by how the dark matter acts, by the growth of the dark matter halos and by the merging of those halos. And also that one way of thinking about the formation of a galaxy is thinking about the evolution of little teeny overdense universes as they expand, stop expanding, and then turn around and collapse. The next thing is to remind ourselves of the diversity of galaxies. We looked at this on Thursday, but I wanted to remind you that there are a couple of important tools here. First of all, the expansion of the universe means that distant galaxies' light is redshifted. And the finite speed of light means that as we look further away, we're looking further back in time. So you remember this concept of look-back time, that if I look at something 8 billion light years away, I'm looking 8 billion years ago. And so the kind of data that I take when I look at the universe is like a geological ice core. The galaxies that are further away in this image, the Hubble Ultra-Deep Field, I'm looking back in time to earlier stages in the history of the universe. And so everything you see here is light from ancient galaxies. These are perhaps only 5 or 6 billion years ago, whereas some of these very small and red galaxies may be as many as 9, 10, 11 billion years in the past. And when one does this, one can see, one can look at the evolution of the galaxy population. This is, in fact, what I do for a lot of my research. And you end up seeing kind of systematic trends in the properties of galaxies with time. Younger galaxies are kind of smaller, clumpier, messier, and more gas-rich. If you come towards the present day, they become, typical galaxies become rather more orderly in their structure, and you get more and more recognizable spiral galaxies with a nice settled disk, and more elliptical galaxies with a spheroid of stars. And so just reminding everyone, remember that most galaxies have a disk. That was one of the observational results. If you look around in the universe, most of the galaxies we see have a rotating disk of stars. And so this is something that we'll want to explain. Some galaxies, though, many of them, but not all of them, have a large spheroid or bulge. We called them elliptical galaxies, and these have basically, instead of a rotating disk of stars, they have more random motions of the stellar component in the galaxies. And we're going to need to, and these lack significant cold gas and star formation, and we're going to need to explain why that is. And then a final result, which we haven't talked about yet much, but you saw it when you were thinking about galaxy clusters, is that actually only 10% of normal matter makes it into stars and cold gas. Most of the mass in the universe is hot gas. And we're going to need to explain why that is.